Welcome to the Rich Report, a podcast with news and information on high-performance computing. Today, my guest is Minesh Amin. Minesh is the CEO and founder of a company called MBA Sciences. They put out a product called Parallelism. So Minesh, welcome to the show. Why don't we just get started by going through your slides?
Okay, so we'll be talking about SPM.Python, a parallel scalable version of Python that can be used to exploit parallelism across servers, cores, and GPUs, which is what makes it unprecedented. And so over the next 10 slides, we'll be talking about the what, why, and how we went about doing this. So on to the next slide on exploiting parallelism with SPM.Python. So as I mentioned, this allows one to leverage parallelism across servers, cores, and GPUs, but in a fault-tolerant manner. And of course, we are dealing with two very different sets of instruction sets, so there are issues with respect to that. And right now, our interface to the GPU world is by way of PyCUDA. So that's basically the main the thing that is kind of unique about this. That, you know, across the board, people don't have to pick and choose and be stuck with a particular choice. They can go back and forth. The other thing about SPM.Python is, so what are the two ways by which people can use Python? And I have actually used it. The most obvious way is to parallelize Python scripts, because it's, after all, a parallel version of Python. And you can leverage, parallelize Python scripts across cores, both within and across servers. So that's the most obvious way of leveraging this capability. The other less obvious way is to actually have SPM.Python launch, track, and monitor any standalone application out there. So for example, launching GCC compilers in parallel, or launching a parallel application written in OpenMPI, for example, to be able to launch that in parallel. Now, why would you do that? The reason is SPM.Python has fault tolerance baked in, so that it can, all these other applications, they would benefit from the fault tolerance by osmosis. They don't have to write a single line of code for fault tolerance. Just by the virtue of how it is actually launched, they benefit from it. So those are the two ways by which SPM.Python can be leveraged. So going on to the third slide. So before we go into the details of it, let's take a step back and review what is the challenge, what is the context within which this capability has been designed, architected, and implemented. Well, my contention is that the buzz around cloud computing and cluster computing notwithstanding, the dirty secret is this, that the most productive software engineers will be the ones today and into the future, will be the ones who can produce quality parallel software in a serial-like environment. That is, even if you have a software engineer who's expected to produce parallel software that's meant to scale to, say, 100 cores or 100 GPU cards, they will never have access to that much resources on a 24/7 basis. They will always be doing the bulk of the development in a serial-like environment. So there will always be this disconnect between where the work gets done in terms of the maintenance and the authorship and all that, and where the end result eventually gets deployed. So therefore, you have this difference between the development environment and the deployment environment. And that is my contention, that this is what is happening today, and this will continue to be with us for the foreseeable future. So now then the question becomes, if I'm a software developer and I'm expected to produce parallel capabilities in a serial-like environment, it sounds like there's free lunch involved here. How am I possibly going to make anything out of it in a productive way? And so what I'm claiming is that if this is given, if this is true, then the only choice we have as an industry going forward is if we have ways by which we can exploit parallelism by expressing it in terms of primitives, parallel primitives, that shelter us from the differences between the serial world and the parallel cluster. So it is the primitive's jobs to account for the fact that on a laptop you only have 2 cores, and on a cluster you will have 100 cores. And as a developer, I will focus on just the serial component of a parallel application. So that is my main contention, that we have this disconnect, and therefore all parallel software engineers will have to express their parallelism in terms of parallel primitives that will hide the details between the serial world and the clustered world. Okay, so going to the fourth slide. So what does that mean with respect to our solution? It's fairly what is the essence of our solution? If that statement is true, that the parallel software engineers will have to produce parallel software by expressing parallelism in terms of primitives, then as a provider of such a capability, our job is fairly straightforward to state. And that is, we want our customers to do simple things simply. There's a classic example of hello world in Python, which is like one line, while in Java it's like 5 lines or 10 lines. So in the parallel world, it's something equivalent. We want people to express simple ideas simply, and we want them to leverage existing technology and applications. We don't want them to rip out anything. At the same time, we want to provide them with the power and flexibility to solve more sophisticated things down the line. So we don't believe in this idea that everything has to be expressed in terms of, say, MapReduce, and that there is no other way of doing things. Actually, that is the biggest fallacy around. So the idea here is, okay, MapReduce is important today, but tomorrow you will need more sophisticated forms of parallelism. When that need arises, you shouldn't have to rip out anything. It should be a natural progression of whatever is already there. So that is our goal, to enable all these things. And we do it by way of 3 essential features. One is, as I mentioned with respect to the challenge, we provide a range of suites, parallel primitives, that allow people to express parallelism. Because that's the only way software engineers will be able to produce parallel software. So, we have to provide them with primitives. So that's the first set. The other one is package management. It may sound boring, but it's one of the most important things when it comes to parallel software, because we are dealing with at least 3 environments: the laptop, the mini cluster close to the laptop, and then the official cloud. And each time you have a different environment, you have the setup issues and the packages that are available here and not there, and those kinds of things. So we have streamlined the whole process by including within Python itself a package management system, and we'll see what that means shortly. And the third feature is this notion of methodology. With SPM.Python, unlike all other alternatives there, including Hadoop, we provide, in this current release, 9 task managers. So using MapReduce as an example, MapReduce, using our terminology, is just one task manager, and we provide 9 of them. So now the question is, from a developer's point of view, how would they know which of these 9 to select to solve a particular problem? So we have this notion of we provide this methodology that allows people to capture the essence of their problem in terms of patterns. Just like in the serial world, you have design patterns. Here we have parallel management patterns. And so you take your problem, you map it to one of these 9 patterns that we have. And the minute you are comfortable with that, you are now delta step away from having a working prototype, because those patterns are how the API comes from the other direction towards the patterns, and the developer is coming from the intent towards the patterns from the other direction. And that's how the 2 merge. Make sense? Okay. So that's why we have these 3 components. And again, the reason for having these 3 components is that we have the additional burden because we have multiple primitives. So we want people to not simply throw the primitives at them and say, well, you're on your own. We want to provide them some context, because although we may provide you 9 primitives for a given problem, you only need 1 of them. So what are the other 8 doing? So we don't want them to be overwhelmed by the fact that there are these other 8 sitting around. If they don't need them, they should not even get in their way. So, okay, on to the next slide. So now let's review each one of the features quickly. The first one is, of course, the technical anatomy of SPM.Python. How is this whole thing possible when we talk about primitives? Well, we take the original Python language and we augment it with 2 kinds of features. We provide 2 kinds of primitives: parallel primitives, parallel manager primitives that capture the top-down view of a project, parallel capability, and communication primitives that capture the bottom-up view of a parallel capability. And then we do one additional thing. We couple these two things together because we want to provide these features in a way where the deadlocks are eliminated. So if you go through our documentation, there's not one place we mention, oh, there's a potential for a deadlock here. We have gone out of our way to track every one of them and trap them, should they ever occur. So we want people to use these things. So, for example, if somebody were to exploit coarse-grained parallelism, where communication is disabled, then the fact that they're using a coarse-grained parallel primitive means that communication primitives are completely disabled. Now, should they violate that assumption and go ahead and attempt to use it anyway, the infrastructure will throw an exception, saying that you're using this parallel task manager. It's a coarse-grained thing. You're not allowed to use this communication primitive. Exception. End of story. There's no way you can proceed beyond that. So, and that is what the guts of the patent is all about. So that's basically the technical analogy. The fact that we augment the Python language with these two kinds of primitives and a couple of other issues that are kind of low level, having to do with exception handling. None of these things, by the way, have ever been attempted in any other language that I know of. So that's why this is not a library solution. It's actually a complete distribution. Going to the next slide, titled Built-in Package Management. Now, why is package management required? Well, we want this to be easy to install on any machine. And because this is a parallel software, it's meant to install on multiple machines and multiple clouds. We want that to be very straightforward. So we have architected in such a way that you can actually have multiple versions of SPM.Python in the same directory and it will not conflict. It can also reside with existing Python distributions and it will not conflict. It will not use somebody else's distribution and somebody else will not be able to use our stuff. So that's how it is protected. And the reason is we don't want people to go through the hassle of figuring out what works where and what the path is and what not. The other thing is that each distribution contains both 32 and 64-bit binaries. So it's the same path, but depending on which machine it gets invoked on, it will figure out which binary to use. And the logic carries over all the way to PyCUDA. Because in case of PyCUDA depends on CUDA, which, there are like 4 versions that are in wide use today. CUDA 3.0, 1, 3.1, 3.2, and now 4.0. So depending on which machine has which version, it will figure out in real time which package to use. The whole philosophy is, if you take any other package management, including on Linux or anything, they're all designed with the principle that under each directory, there should be only one version of something. If you have multiple versions, the system gets confused. But what they have done is now, from a developer's point of view, it's a pain now, because different machines means that you have to point to different paths in order for the whole thing to work. And what we have done is we have turned the whole thing on its head. We have said, under every single directory, I should be able to put as many versions as I want, as long as only one version is active at any moment in time within a single resource. That's the key part here, not the fact that there are multiple versions in the same directory. Make sense? And so that streamlines the whole process. And then, of course, the third feature is the parallel management patterns. As I mentioned, our burden is the fact that we provide 9 primitives, 9 kinds of task managers, and 4 additional communication primitives. Now, as far as the developer is concerned, if you take any parallel project, you only need one task manager. You don't need multiple task managers. So what are the other 8 doing? So what these primitives do, these patterns do, is they help you to define your problems in an easy-to-relate way, just like design patterns. Design patterns, they capture the bottom-up view of a serial capability in terms of proxy pointers and whatnot. This one captures the top-down view of your parallel capability in terms of the very essence of what it is that you're trying to do. And then once you have described your problem in terms of these patterns, then it's a delta step away from the actual primitive that you have to use from SPM itself. So our documentation takes advantage of this. We don't talk about solving problems by straight away going into the SPM API. We first describe the problem in a way that anybody can relate to. Then we introduce the pattern, which is again and something that anybody can relate to. And then we give, oh, by the way, this is how you write the code to convert that pattern into a fault-tolerant version of a working piece of code. Make sense? Basically, that's the approach we take. Now, again, in a whole comprehensive way, because the burden on us is, we have 8, 9 patterns People are only interested in one. Of course, different people will be interested in different patterns or different parallel managers, but that's a different story. Which leads us to the next slide, which is what's the big point about all of these things taken together. What it allows is, for the first time, and the reason we are so excited about it, is you can literally go from 0 to 512 of any combination of 512 servers, cores, or GPUs in under 100 lines of Python, plus PyCUDA. Any combination. You can have 10 servers plus 4 cores within servers plus 4 GPUs, all that. As long as it adds up to 512, you can exercise any of these things with at least, starting with as little as 100 lines of code. What are the kinds of problems that you can solve? Well, there are 7 patterns that I've described on that page. The top one is called clone once. So that is, for example, if you were upgrading a software stack on a machine, and you finalize exactly the steps to follow for that software stack. And somebody tells you, oh, by the way, upgrade the cluster. Well, that's a clone job, because whatever you did on one machine, you're going to repeat it 100 times. So that pattern says, whatever you did on one machine, do it as many times as their machine. So that's basically clone once. Clone once per machine. You have another pattern on the left-hand side called clone repeat. This is an example that occurs when monitoring machines. You're doing something once, but you're sleeping and repeating it again. And there are 2 ways by which to solve it. Then you have on the extreme right-hand side, on the top side, it's called partition list, where you have a list of things you want to execute. Examples include regressions or what-if analysis of all kinds of things. You have a list of things you want to execute. It doesn't matter in which order, as long as they get executed. Well, that's a list of things. So in our documentation, we start with this diagram, and we mention that in life sciences, it shows up in this context. In system administration, it shows up in this context. So in the very next pages, you get a sense of what this pattern is all about. And then in the subsequent 4, 5, 6 pages, we describe these 40 or 80 lines of code. And that's how we bring along the user from zero knowledge about parallelism to coming up with fault-tolerant capabilities literally in minutes. And then 7 patterns. And you can imagine, out of these 7, MapReduce is just one of them, which is this partition aggregate decentralized, which is, you apply a filter, and then you do a reduce operation, and then you produce a report. So according to this terminology, MapReduce is just one of 7 things. The one at the bottom is an interesting one. It's called partition grid. There, what is happening is that it shows up in the context of OpenMPI. And the thing that makes that particular pattern unusual is that, unlike the other patterns, partition grid is treating n resources as a single unit. Thereby, so for example, if one of them goes down, all the others are supposed to be forcibly shut down. Otherwise, you have a deadlock, because they are all working on the same problem collectively. While if you take any one of the other patterns, if one of the machine goes down, it has no bearing on any of the other machines that are active at that moment in time. So the fault tolerance and the ramifications of a failure have totally different meaning depending on the pattern that you're talking about. Does that make sense? Yeah. So with OpenMPI, that is at the bottom. Now, these 7 patterns, believe it or not, cover the vast majority of stuff that's out there. Vast majority, for everything from life sciences to EDA. This is by no means the only. There are 3, 4 others that I can think of, but this is like a starting point. And within these, you have flavors. You have coarse-grained versions and fine-grained versions. Coarse-grained meaning that the task cannot communicate with anybody, while fine-grained means that they can only communicate with the master, for example. Because remember, we want to make sure no deadlocks occur, right? So if you look at this diagram, it says that it has certain implications in terms of the communication primitives that you can use. So for example, in case of cloning, there is no communication primitive. You're simply sending back the status report. In case of the partition grid, communication primitives are allowed, but in a kind of a grid structure. with the stipulation that if one of them goes down, all the others are forcibly shut down. So that's basically the big picture. So now if we go to the next slide, which is the advanced technology highlights, there are two parts here. One is the patent, which is going to be issued on Tuesday. So what's the patent all about? Well, it captures in a way that three parts. There are, I think, 20 claims. But the three main critical things about it are tracking of resources, coupling of task managers with communication primitives. Because my claim is that this is the only way to eliminate the vast majority of the deadlocks. So, for example, if I'm managing 10 resources that are communicating as a grid, then that has certain bearings on me as a parallel manager. I have to treat all those 10 resources as a unit, because otherwise I will have a deadlock. If, on the other hand, I'm managing 10 resources that happen to be executing 10 C compiles in parallel, then one of them fails. It has no bearing on the other 9. So the claim here in the patent is that there should be a coupling between the task managers and the communication primitives, that they are in fact two sides of the same coin. If I want to be able to communicate in my project to my left, right, and south, north neighbors, it is for whatever reason, because of some data structure related issues or something like that, I cannot just go ahead and start issuing those send receive calls. It has bearing on how the task manager is going to manage not just me, but all my neighbors. I cannot simply say that I want to communicate with my left neighbor and just call it a day. I have to convey that information to the task manager and say, by the way, I'm communicating with my left neighbor. So that means that if I go down or my left neighbor goes down, the parallel manager has to be shut both of us down. You see what I'm saying? Okay, so that's the second point of the thing. And of course, the third part is the filtering of scale messages. You can imagine when the resources are forcibly shut down and relaunched, the reason they have to be relaunched is that when you're talking about not resources at national labs, but in any other situation outside of national labs, just because you ask for 40 machines, you're not going to get them at the same time. You may get 10 now, 5 later on, 5 sometime down the line, and maybe on certain days you will never get 40. So then what happens is, if it took you 1 hour to get the 10th machine, and within 5 minutes you code dumped, it's not right to actually give that machine up so quickly when you have all the other things to do. It's still in the pipeline. So you say, well, okay, I have to shut it down because there was a code dump or something like that, but I want to relaunch it without giving up that machine because it took me 1 hour to get hold of it. Well, if I'm going to relaunch it, I have to be very, very careful because otherwise I have stale messages that are going to the new incarnation that was actually meant for the previous incarnation. And so the patent talks about why that is important and how to go about doing that. And of course, the other part is we were recognized at supercomputing and just recently 3 weeks ago at PyCon. So basically that's the gist of it, and that's why we are in a position where we are, which is to have a comprehensive solution. And thanks to the technology, it's not a pipe dream anymore. It's really real and exposed in the real world. So the wish would be that the audience come by and try us out at the website. Come by and download the trial edition. We have links to the white paper we co-authored with Intel. There's an interview that we had with Intel at SC10. And of course, the website will have the technical briefs for each one of these patents. And for each one of these patents, we have a technical brief that describes just 20, 30, 40 lines of code over 6 pages. Now, it may seem like a lot, but we are using a visual representation of how to show you what gets executed when. And all that is available, will be available on the website on April the 12th. And with that, I yield the floor.
Well, thank you, Minesh. That was helpful. I learned a few things about Parallel Python here. I did want to ask you about the SC10 show. That's kind of when you first really premiered this, correct? At the disruptive technology section of the show floor. And what kind of reaction did you get from people at SC10?
It ran the gambit from are we using, what was the underlying messaging libraries, to how do we ensure deadlocks are eliminated, to why are we calling it parallel management patterns? What has management got to do with anything? Why not just call it parallel patterns? And we went into the definitions of it. There was a lot of interest in OpenMPI and how this could be leveraged in the context of OpenMPI. There was a lot of interest in using Python already has hooks to OpenMPI. The problem is when exceptions are thrown, you have deadlocks. So there were situations where people were interested in trying that out. So there was a lot of interest in the fault-tolerant aspects of things because there are some fairly strong claims that we are making.
Yeah.
And we are right now, even now as we speak, I'm in the process of one by one going over all those issues and giving custom builds to people who can actually try it out. Because from January onwards, originally after I came back from SE10, the focus was on OpenMPI. But then after December break, we quickly changed focus for CUDA because of some other reasons. Now that CUDA is out of the way, we are going back to OpenMPI and showing to people, the SE10 customers or potential customers, the power of this thing. That even when you have OpenMPI, this thing can actually help you leverage parallelism without you having to write any fault-tolerant code in OpenMPI, because that's the reason why people use OpenMPI, right? They use it for performance reasons. They don't use it for fault tolerance. But the problem is, on any machine, any application, parallel application, you must have fault tolerance. So to answer your question, it was very gratifying that people latched on to the most critical aspect of it, which is that how we go about providing fault tolerance in all these contexts.
So you have this resource management capability built in, right? Does it work potentially with resource managers like, say, Platform or Condor? Would there be any reason you couldn't use it with those kinds of things?
So what we do is, from our perspective, think of it this way. From our perspective, we encourage our developers. Remember, the goal was to express parallelism in terms of primitives. But there is this other goal also, which is that we want people to write code in a way that is independent, is a function of a handle to a pool of resources, not the content to a pool of resources. Because the handle is the only thing that is the same whether you're on the laptop or on a cluster. It's the same handle. It's the content that is different. On a laptop, it will be made up of 2 cores, the content of the pool, and on the cluster, it will be made up of 100 cores. So, for example, the programming style and the primitives and all that, they don't allow you to say, I want you to run this on this particular core. I don't give you that flexibility. So the whole thing is isolated from it. So now what does that mean? That means that, for example, if you have to interface with Platform, SPM.Python is interfacing with Platform to only get hold of the resources, nothing else. So it is whether I'm interacting with the Platform or I'm interacting with machines via SSH directly. As far as the developer is concerned, it's the same one call. And once the resources arrives on the back end of SPM.Python, it takes over the management. At that point, it doesn't really matter where the resource came from, whether it was because of SSH or Platform, we take over the whole thing. The only thing we have to be a bit clever about is that if the resource came from Platform and we want to relaunch things, we have to do it in such a way that Platform doesn't think of it, oh, this resource is given up, let's give it another job.
Yeah.
So in that context, what we have to do is we have to fool Platform into thinking that it is launching a piece of job that is actually the daemon of Python, or SPM.Python, not Python, SPM.Python itself. And then as long as the daemon is alive, the Platform is happy. And then we can, under the hood, relaunch as many times as we wish. Because we don't want to confuse Platform, right? Or for that matter, any grid infrastructure, whether it's from Sun or Intel, it's the same philosophy. So to answer your question, from our perspective, Platform may have all the bells and whistles in terms of management and all those things. Once the machines come and land on our lap, we take over ownership of it. And we don't rely on Platform at all.
That's interesting. So in terms of speed, a question about, speed up. I was at a Open Fabrics workshop this week, Minesh, and this guy presented on Python for RDMA management. right? And the first thing that comes out of his mouth is, I apologize that Python is so slow, but it does all these things, right? And this guy was from Obsidian. So was speed really the thing that drove you to develop this, or was it the fault tolerance? How did that come into play?
Well, we have originally the company started with the intention of having a business model around the C++ library. That's what we came out with in 2007, after a year and a half worth of development. And I quickly realized that as a self-funded company, there is no way I'll be able to make a business out of it, because if I'm going to sell a library to somebody, they cannot see the value proposition of it immediately. They have to add their own things on top of it to make it an application and then see how powerful this thing is. So then I decided that, well, there was no way I would run out of money with all this. So I went dark and started going after dynamic languages. So initially started with Tcl and made another switch, went from Tcl to Python. So Tcl is available, but we don't make it available to, it's not generally available. If somebody were to make it worth my while, I would make it available to them. But right now the focus is Python. So what is the infrastructure? We can process, for example, I think it's like 30 microseconds per message, which is unbelievably fast. One message, it takes 30 microseconds to pack and ship off. Wall Street is working at with a limit of around 100 microseconds. I'm at 30. Now, the reason it is so fast is because the backend infrastructure, having to do with fault tolerance, having to do with packing and unpacking of messages and filtering and all of it is written in C++. And the reason for that is because the irony in all of this is that infrastructure, that piece of code, is heavily type-centric. So I need a static, strictly typed language to write that code. I cannot write it in dynamic language. It will become a maintenance nightmare. Because there's, I kid you not, for SPM.Python, just the back end of it, there are over 900 types. I'm exercising GCC compile. If I were to share some of the statistics, nobody would believe me. But there are over 900 types. Now, if I were to write that code in Python, all that type infrastructure, all that type information that is embedded within types is lost because everything is dynamic, which means that I have to express the code in a runtime fashion and make it it makes it very, very complicated, and, business proposition, it becomes a huge nightmare. So all that is written in C++. I can't even use C there because I don't want casting of pointers. I want the compiler to go through the official, the documented way of virtual functions and all those things. And of course, it has to be done in a way that is extremely fast. So the long story is, this thing is written in C++ mainly for selfish reasons, namely that I don't want to spend a lot of time testing this thing. And most of the code that I've written is control-centric. And because it's control-centric, I want to use a static language, a strongly typed static language. And so that's the way it is implemented. And the side effect of it is that it's unbelievably fast. The other thing is, this code is written in a way where every assumption that goes into the parallel component is actually embedded within the code itself. And the reason is, when you run my software on your machine, and for some reason it crashes on you, I have to produce a stack report. And when you give me that stack report, I should be able to fix it without having to reproduce it. That's a profound statement to make. Take any software from anywhere in the world, open source, commercial, in the serial context. What happens? I file a bug to you. You will tell me, oh, give me a test case. So I give you a test case. What do you do on your end? Basically reproduce it. Only when you reproduce it, you are going to fix it. If you cannot reproduce it, you're going to flag it saying, cannot reproduce it, this is not a bug. But when it comes to parallel software, you are running it on my software on your 100 machines, and I have access to 100 machines. Doesn't mean I'll be able to reproduce it. So that means that for me to fix the problem, I have to fix it without having to reproduce it. I have to simply go by the stack trace that you're producing. I can't even ask you for a test case. I can't even ask you to log into your machines to find out what is going on. I have to literally write the code in a way that it's self-testing. It's embedded within itself. So that stack trace is actually telling me when I went down, this particular assumption was violated, and this was the status of the machines and the systems and all that. On my end, I go into my code, figure out the line number, all that from the stack trace, by the way. And that stack trace cannot be very deep because this is multi-threaded. GCC has all kinds of issues producing stack traces for multi-threaded code. So I have no more than like half a kilobytes worth of memory within which the whole thing has to be packed. And so the story here is that I have to be able to fix this thing without having to reproduce it. That's what makes this thing extremely, extremely hard. And it took me 5 years to get to this point. And finally, it's been 2 years. There has not been one case where I haven't been able to fix a problem. I've never had to go to a customer or potential customer and say, please give me a test case. That's how this thing was architected. But it took a while to get here. You see what I'm saying?
Yeah, yeah.
Because the fundamental thing here is that there is no such thing as a parallel debugger. Or to be more precise, there is no such thing as a parallel x86 control-centric debugger. You have serial debuggers, yes. You have order 1 debuggers that allow you to trace a handful of threads on a particular machine or a server. So 4 years ago, the handful was like 2 cores, and today it's 8 cores, and maybe 2 years from now it will be 16. But SPM.Python scales to 512 cores. There is no debugger. I don't care what total view says. There is no way the debugger can be launched and I have any hope of reproducing the problem because it will perturb the system to such a degree. Because the other thing is that all of this is asynchronous. It's not centralized. Everything is asynchronous. So there's a lot of magic happening at the back, but that's the good thing. Unless when you ask me, in fact, I haven't had this kind of a discussion in over a year now, because it's a pleasure for me to focus on the front end of it, as long as people don't ask me about the back end of it, because it's kind of hellish, but in a good way, right? Otherwise, there's no business here.
Right, right.
If it was straightforward or something like that, people would have done it by now. And even open source. Open source is problematic because the same fundamental issues still are there. Whether it's open source or not is besides the point. And trust me, from my own experience, no open source guy is going to do this for pro bono. It's hellish to debug these things.
Yeah, yeah.
You want to be compensated for it. Oh, no. What happens is our focus, now that CUDA is there, the next release, June timeframe, we are going to activate OpenMPI. Right now, it's limited beta. But that pattern that I described where OpenMPI is, end resources are treated as a single unit, right now it's only limited beta, but we'll make it general availability. And around September timeframe, we have this notion of hierarchical SPM, where each spoke, a hub talks to up to 512 spokes. Each spoke can turn around and become a master for subsequent 512 spokes. And from that point on, there is no limit.
Yeah.
And now you have a hierarchy. Now, the hierarchy right now is not this, but I can imagine the hierarchy playing a bigger and bigger role, especially when you have merging of x86 and GPU for the following reason. Imagine you have 64 servers of flooded with GPU cards. Well, I can imagine the first level of the hierarchy would be made up of one hub, and then it talks to 64 spokes because there are 64 servers, and then within each one of them, it will equal to on average, if each server has 4 GPU cards, you will have 4 spokes within the second level, talking to individual cards. And that's how you establish a hierarchy, just in the context of GPU x86. And of course, you can have hierarchy in the other context too. So when I was at SC10, one of the things some of the research labs found it very curious. It was kind of very flattering because they said that this was the only way they knew of on how to write parallel code that will scale all the way to exascale. And you know why that makes sense now, right?
Yeah.
Because this is the only way you can hierarchically go to exascale. And you must have hierarchy when you go to exascale. You can't treat tens or thousands of servers in a flat way, because it's virtually guaranteed that some of them will be always down.
Right.
So you need a way by which you create subgraphs of the 10,000. And the minute you have subgraphs, you have hierarchy. So there were a couple of guys from France and the UK who are interested in pursuing this further. I don't know where it will lead to, but they had some rather astonishing things to say about that to me. They have familiar with what the other labs are doing in the U.S., and of course they're familiar with what CERN is doing in Switzerland. But the one guy from Paris was telling me that this is the only way he knows of that will actually scale. And up to now, it was at the back of my mind, but for him to say that to me flat out was, oh, okay, this is interesting. So to answer your question, the hierarchy will be the way by which we overcome Phi 12.
Well, good, Minesh. I think just a quick wrap-up question. How do you enjoy being an entrepreneur here in the HPC space?
I count my lucky stars. I come from Zambia, which is a third world country.
Yeah.
And I got exposed to computers when I was a couple of weeks shy of turning 20. And up to that point, I had never touched a computer. So when I turned 20 is when I took Introduction to Programming in Pascal. That's when my journey began. And for me to be in this position where I'm not only on the receiving ends of these accolades, but clearly working on something that is not a derivative, it is really, really bleeding edge. I mean, of course, you expect me to say that, but take other people's word for it. And to be doing all this cutting edge, coming from a third world, and starting so late in the game, I like I said, I count my lucky stars.
Well, thank you for coming on the show today, Minesh, and congratulations on the patent. I think this is exciting stuff, and I think that our listeners will really appreciate what you're doing. So, you bet. Okay, folks, well, that's it for the Rich Report. Stay tuned for more news and information on high-performance computing.